What's up everyone? It's Stack Lessons here. Welcome back to the channel. Today we're diving into production patterns, 10 decisions senior Databricks GenAI engineers get right. Let's get into it. A team shipped a customer support agent on Databricks. 6 weeks later, a prompt injection in an inbound ticket convinced the agent to read the CRM and email the customer record to the attacker. By the end of this video, you'll know the 10 decisions senior Databricks GenAI engineers get right on every build, the ones that would have caught that breach before it shipped, and the qualifier word that picks the right answer when two options both look correct. 3 failure modes you'll see if these decisions are skipped. First, cost overrun. A team picks a storage-optimized vector search endpoint for a low-latency chat app, then rewrites 6 months in when the latency budget breaks. Second, audit failure. A third-party model gets called direct from application code, so when compliance asks for a record of every prompt, there isn't one. Third, the injection breach we just opened with, untrusted input, sensitive data, and external action all sitting in one agent session. Each of these traces back to a single decision someone made wrong. Let's walk all 10. 4 terms anchor everything in this video. A decision qualifier word is the adjective that picks between two technically correct answers, phrases like least overhead or lowest latency. The data plane is where compute and the model actually live. The control plane is where policy and audit sit on top. Defense in depth means stacking independent guardrails, so a miss in one layer gets caught by the next. And the lethal trifecta, which we met in the governance episode, is the failure condition the agent rule of 2 prevents. Here's the premise of this episode. The thing that turns a working prototype into a production system on Databricks isn't a single big architecture choice, it's 10 small decisions, made over and over, where the wrong answer quietly burns budget, breaks an SLA, or fails an audit. Senior engineers don't memorize answers, they've internalized the qualifier word that points at the right one. Here are the 10 we'll walk. The agent rule of 2, your threat boundary, vector search endpoint type, cost against latency, scorers versus judges, pick by how deterministic the check is, MCP host, managed, external, or custom, registration interface, PyFunc, ChatModel, or responses agent, AI gateway versus model serving, control plane against data plane, the RAG Eval Triad, diagnosing which leg failed, the guardrail boundary, hallucination versus prompt injection, Unity catalog lineage, what you get for free versus what you have to instrument, and the qualifier words that disambiguate every other decision, about 90 seconds each, and the shape is the same every time. Production scenario, common engineering miss, then the right pattern in one line. One pattern for the whole episode. Start with the scenario someone actually hit in production. Name the common engineering miss, what feels right, but isn't. Then the underlying reason it fails. And finally, the right pattern, distilled to a single line you can carry into a code review. Let's start. We'll hit each decision the same way, the production scenario, the common miss, then the right pattern in one line. Decision 1. A team builds a customer support agent. It reads every inbound ticket, that's untrusted input, written by anyone on the internet. It looks up the customer in the CRM, that's sensitive data, and it replies to the customer over email, that's external action that leaves the building. All 3 capabilities stored in one agent session, and the team ships it because the demo works beautifully. The common miss is treating those 3 capabilities as features to add, instead of as risks to budget. The agent rule of 2, which we introduced back in episode 17, comes from Meta's threat model and is now in the Databricks AI security framework. An agent session should hold at most 2 of 3 properties: untrusted input, sensitive data, and external action. Hold all 3 at once and you've got the lethal trifecta. A prompt injection in the ticket can read the CRM and email the result to the attacker, without anyone touching a keyboard. Think of a bank teller. They can read your account, accept any walk-in, or move money out, but never all three unsupervised. Move money for a stranger off untrusted instructions, and the bank gets robbed. The right pattern isn't to scrap the agent, it's to drop one leg. Usually the cheapest one to drop is external action. Wrap the email step in human approval, and now the agent can draft a reply, but a human clicks send. Untrusted input is still there, sensitive data is still there, but the attack chain breaks. And notice, the rule of two is a per-agent design constraint, not a platform-wide deny rule. Single-tenant internal agents that hold all three on trusted data are fine. Read what the agent can do, not who's using it. Decision 2. A team builds an enterprise knowledge agent over 1.3 billion vectors of archival content. The workload is batch and moderate queries per second, with no hard latency contract. They default to standard endpoints because that's what every tutorial uses. First month's invoice arrives at around $47,000, and a project review opens the next quarter. The common miss is picking the endpoint type from familiarity, not from workload shape. Look at the numbers. At 1.3 billion vectors, standard runs around $47,000 a month. Storage optimized runs around $7,000 for the same corpus, roughly 7 times cheaper per vector. The price for that savings is latency. The standard query floor is in the tens of milliseconds, while storage optimized adds about 250 milliseconds because vectors aren't held hot in memory all the time. For an interactive chat agent, that quarter second is noticeable. For batch and archival retrieval, nobody can tell. Paraphrasing the Databricks vector search documentation, choose storage optimized when you've got 10 million or more vectors, can tolerate the extra latency, and need cost efficiency per vector. 3 conditions, all 3 required. Miss anyone? Say you're under 10 million vectors, or you have a strict latency SLA, or you're under regulated workloads that need customer-managed keys or FedRAMP, and you're on standard. The right pattern is to match the endpoint shape to the workload shape, not to the tutorial. Interactive chat, low millisecond budgets, customer-managed keys, FedRAMP, standard. Large archival or batch retrieval where 250 milliseconds is invisible, storage optimized. Datadino's callback in episode 8 is a useful example. They had a contractual 200 millisecond budget, which disqualified storage optimized on its own, regardless of corpus size. Decision 3. A team has an Eval suite running nightly, and their Eval cost just jumped roughly 8 times. Here's what happened. They wanted to verify 2 new things. Every answer cites a source, and every answer stays under 500 tokens. The judge framework feels powerful, so they wrote an LLM judge for both. The common miss is using a language model to do a regex's job. Format and length aren't subjective, they're deterministic checks, and a judge call is the wrong tool. Get the hierarchy straight. A scorer is any function that reads a trace and returns a quality signal. A judge is a scorer that happens to be powered by a language model, retrieval groundedness, relevance to query, correctness. Metrics are what you get when scorer outputs are aggregated across a run, pass rate, average score, latency percentile. Every judge is a scorer. Not every scorer is a judge. Think of a school. The rubric is the scorer, the teacher reading the essay is the judge, and the report card average is the metric. The right pattern is simple: deterministic checks, latency, schema, token count, regex, citation present. Those are code-based scorers, written with the @scorer decorator. Subjective qualities, faithfulness, relevance, tone, correctness, those are LLM judges. Pick by whether the question has a deterministic answer, not by which API you find more interesting. The cheaper tool that gives a definite yes or no almost always wins. Decision 4. An agent needs 2 tools. Tool A is a vector search index the team already owns in Unity Catalog. Tool B is a partner REST API behind a static bearer token. A new engineer reaches for custom MCP and decides to host both as a Databricks app. 3 weeks of work disappears into hosting code that already exists upstream. The common miss is using custom MCP as the default, when it should be the option you pick only when nothing else fits. 2 flavors to compare here. In order of effort. Managed MCP wraps things Databricks already governs: Unity Catalog functions, vector search indexes, Genie spaces. UC grants enforce permissions automatically, which means the lowest implementation effort of the bunch, and it's the default whenever the tool is Databricks native. External MCP proxies third-party APIs through a UC HTTP connection. The credential lives in Unity Catalog. The Databricks proxy injects it on every outbound call, and the agent never sees the secret. You can use a shared principal or per-user OAuth, depending on whether you need identity pass-through. That makes external the right choice for third-party APIs you want to keep under governance. For our scenario, Tool A is a managed MCP server and Tool B is an external MCP server. Total infrastructure code, 0. Custom MCP has its place, but it's narrow. Reach for it when the tool logic doesn't exist anywhere yet. A stateful workflow, a wrapper around a legacy system that needs auth gymnastics, or something that doesn't fit the HTTP proxy shape. The right pattern: try managed first, then external, then custom. Walking that ladder in order is what turns 3 weeks of work into 3 lines of configuration. Quick breath. Notice the through line on the first 4 decisions. They're all resource allocation. Decision 1 was a capability budget, deciding what the agent is allowed to do at all. Decision 2 was a compute budget, deciding which endpoint shape your workload pays for. Decision 3 was an Eval budget, deciding which checks deserve a judge and which can ride on a cheap scorer. And Decision 4 was infrastructure effort, deciding how much custom tooling your team takes on versus inherits. The next 6 decisions shift focus from what you allocate to how you operate. Let's keep going. Decision 5. A team has a working RAG agent and they're ready to register it in Unity Catalog and ship it to model serving. They reach for a tutorial they bookmarked last year, which uses the ChatModel base class in MLflow. The registration works, the endpoint serves, but streaming by default doesn't work the way the docs describe, and the AI gateway inference table they expected stays empty for agent calls. The common miss is registering new agents against an interface that's been deprecated. 3 interfaces, 3 things they unlock. PyFunc is the universal base. It serves anything, but you own the signature, the tracing, and the streaming logic yourself. Under the hood, all 3 log through mlflow.pyfunc.log_model. ChatModel auto inferred a chat completion signature, which was a nice shortcut, but it's now deprecated. Responses agent is the current recommendation. It gives you streaming by default, tool call confirmation, multi-agent support, and native AI gateway inference table integration, with MLflow inferring the signature for you. So for a new agent in 2026, Responses agent is the answer. PyFunc is for non-chat shapes, batch scoring, custom orchestration. ChatModel stays only if you already maintain code against it, and multi-agent supervisors land back on Responses agent. Straight from the official log and register AI agents documentation, Databricks recommends MLflow Responses agent. The phrase that matters is robust logging, tracing, evaluation, deployment, and monitoring. Those are all features that you get wired up automatically when Responses agent is the base class. The right pattern, in one line. New agents go on Responses agent unless they fundamentally aren't chat-shaped. Decision 6. A team ships fast by calling a third-party language model directly from application code. 6 months later, an auditor asks for the inference table and per-tenant chargeback for that traffic. Neither exists. The Unity AI gateway dashboards show 0 rows for those calls, Because the requests never transited a model-serving endpoint. The common miss is thinking AI Gateway is a separate service you can point traffic at. It isn't. It's the control plane wrapped around model serving. Picture an airport. Model serving is the runway and the aircraft. That's where flights actually happen. AI Gateway is the security checkpoint, the gate agent, and the flight recorder layered on top. It doesn't fly the plane, but no passenger reaches a flight without passing through it. The corollary is what trips teams up. Traffic that bypasses serving never reaches the gateway. No inference table row, no per tenant chargeback, no audit. The gateway only governs what actually transits a model-serving endpoint. The right pattern is a one-line rule. Every model call goes through model serving, even third-party models, wrapped as external model endpoints. Now the gateway sees them, the inference table captures them, the audit chain is complete, and policy changes ship without touching application code. Splitting governance from runtime is the entire point of the two-plane design. Decision 7. A team's RAG agent is in production. They track one metric, answer correctness, and it drops from 90% to 81%. The first instinct is to swap the generator for something larger. They spend a week running comparisons. The correctness number barely moves. The common miss is treating correctness as a standalone signal. Correctness is downstream of two other things, and only the triad shows you which one actually failed. 3 legs. 3 different fixes. Retrieval relevance asks whether the retriever found the right documents. When it fails, you change chunking, the embedding model, or the re-ranker. Groundedness asks whether the answer stayed faithful to the documents you did retrieve. When it fails, you tighten the prompt template, enforce citations, or raise the generator's reasoning. Correctness asks whether the final answer is right against ground truth, and it sits downstream of both other legs. Data Dino's numbers from episode 18 are textbook: groundedness 94, relevance 89, sufficiency 76, correctness 81. The retriever wasn't returning enough material, and the model size had nothing to do with it. The right pattern: when correctness slips, read upstream before reaching for a bigger model. If relevance and groundedness are healthy and correctness is still wrong, then the generator is the issue. But most of the time, the retriever or the chunking is what changed, and swapping models is expensive theater. The triad gives you root cause. One metric gives you a number. Decision 8. A team adds Llama Guard at the output and ticks the guardrails box. 2 months later, a retrieved PDF carries injected instructions. They sail past the output filter because the model already executed them on the input side, and a confidently wrong hallucination leaves through the same filter because Llama Guard checks safety categories, not factual grounding. The common miss is treating hallucination and prompt injection as one problem with one guardrail. 2 different threat models, 2 different directions. Hallucination is a faithfulness problem, a benign user, a confused model, an answer not supported by the retrieved sources. You catch it on the response side with grounding, citations, and a groundedness judge that blocks unsupported claims at egress. Prompt injection is a trust problem, adversarial content entering the context, either directly from a user or indirectly through a retrieved document. You catch it on the request side with input classifiers, system prompt isolation, and delimiters around untrusted data. Hallucination is a confused witness. Injection is a planted witness. One you cross-check, the other you screen at the door. The right pattern is layered defense, in 2 directions: request side guardrails for injection, input classifier, system prompt isolation, structured delimiters, response side guardrails for hallucination, grounding enforcement, citation requirements, groundedness scoring. Both configured on AI Gateway, both running on every call. One guardrail isn't a strategy, it's a single point of failure. Decision 9. An auditor wants a full lineage trace, from raw PDF, through chunks, through embeddings, into the vector index, into the registered model that's currently serving. The Spark data frame and Databricks SQL parts of the pipeline show up automatically in Catalog Explorer. The RDD job from 2023 doesn't. The external partner API call doesn't. The training dataset doesn't connect to the registered model. The common miss is assuming Unity Catalog Lineage captures everything by default. Straight from the official Lineage documentation, Unity Catalog captures Lineage automatically for queries run on Databricks, down to the column level, aggregated across every workspace attached to the metastore. The keyword is queries. The Lineage system reads Spark and Databricks SQL query plans. If your data movement happens through a query plan, it's free. If it happens through anything else, it isn't. Think of Unity Catalog Lineage like a hotel keycard log. Every door opened through Spark or Databricks SQL logs itself automatically. The system sees the query plan and records it. But anything that bypasses the card reader, you have to camera yourself. Here's the split. On the free side, Databricks SQL down to the column, Spark data frame reads and writes, notebook and job touchpoints, and the edge from an MLflow run to its registered model. On the manual side, RDD operations from before the data frame APIs, files referenced by raw path instead of through a catalog, and columns derived inside opaque UDFs. For wiring training data to a registered model, one line, mlflow.log_input, does it. And for calls to external systems, use the external Lineage API. Decision 10. This one is meta. It's how you read every other decision. An engineer is staring at a design doc or an exam question. 4 options, all technically valid for the scenario described. Then they notice 3 words at the start of the requirement, with least overhead. 3 of the 4 options disappear instantly, because only one of them is the managed serverless answer. The common miss is reading the options before reading the qualifier. Here's the map. Least overhead points at managed and serverless, foundation model APIs, managed MCP, scale to 0 serving. Lowest latency points at standard vector search and fewest hops, provisioned throughput, no extra proxy. Governance first points at Unity Catalog plus AI Gateway, managed MCP for tools, inference tables for audit, attribute-based access control for data. Cost-optimized points at storage-optimized endpoints, triggered sync, consolidated endpoints, and pay per token over provisioned. The right pattern is to read the qualifier first, then the options. The qualifier is the selector that turns a hard question into an easy one. Here's what people miss. These decisions don't sit in isolation, they couple. 1 and 6 coupled. An agent that passes the rule of 2 on paper still fails audit if traffic routes around serving. 2 and 7 coupled, storage optimized for a latency-sensitive workload shows up as a retrieval leg regression. 3 and 9 coupled, code-based scorers feed the metrics that Lineage proves your model was evaluated on. 4 and 8 coupled, the MCP host you chose determines which guardrail boundary your team actually owns. The decisions are a graph, not a list. Imagine the pull request. 5 additions, all reasonable to the engineer who wrote them. A direct OpenAI call from the app handler. A storage-optimized vector search index for a chat feature. An LLM judge to validate output JSON schema. An agent that reads tickets, queries the CRM, and sends emails, all in one session. And an Eval suite tracking only answer correctness. The senior engineer leaves 5 one-line comments. Route through an external model endpoint. Gateway needs the trace. Use a standard endpoint. This is interactive. Use a regex scorer. The schema is deterministic. Apply the rule of 2. Drop the email send or split the agent. Add the retrieval and grounding scorers. Correctness alone won't tell you which leg broke. 5 comments. 5 decisions, 1 merge. 1 frame to carry into every build. Every one of these 10 decisions is the same underlying question. Are you picking the tool that fits the requirement, or the tool you already know? That's the entire discipline. and it lands on the three promises we opened with. Budget, storage-optimized retrieval past 10 million vectors, code-based scorers instead of expensive judges. SLA, standard endpoints for interactive workloads, rule of 2 on agent capability. Audit, every model call routed through serving, Unity Catalog Lineage instrumented for the gaps Spark doesn't cover. That's the full promise. The same intuition shows up on the certification exam, which is where we'll test it next. Quick 5-question quiz. Question 1. A team is designing a customer support agent that reads inbound tickets from any sender, looks up customer history in the CRM, and replies via email, all in one session. The security review flags risk. Which change best mitigates the risk while preserving the most agent value? Is it A, wrap the outbound email step in human approval so external action requires a person to send? B, block the agent from reading any inbound tickets, eliminating untrusted input entirely? C, switch the language model to a larger one with better instruction following to resist prompt injection? Or D, add an output side llama guard filter on every reply to catch malicious payloads before they leave? Take a moment to think it through. The answer is A. The agent rule of 2 says hold at most 2 of 3 properties: untrusted input, sensitive data, external action, and this agent holds all 3. Wrapping email in human approval drops the external action leg from automatic to confirmed, breaking the lethal trifecta while the agent stays useful. Blocking inbound tickets defeats the agent's purpose. A bigger model doesn't change the threat model, and an output filter can't stop an injection that already executed against the CRM. Question 2. An enterprise has 1.3 billion document chunks in an archival knowledge corpus. Queries run mainly as overnight batch with some interactive use, and there is no hard latency SLA. The team needs the most cost-efficient vector search configuration. Which endpoint type fits best? Is it A, standard endpoint with continuous sync, interactive use needs the lowest possible latency? B, standard endpoint with high QPS enabled, scales to handle the corpus size? C, storage-optimized endpoint with triggered sync, designed for large corpora that tolerate extra latency? Or D, direct vector access index on a standard endpoint, gives the team control over batching? Take a moment. The answer is C. The qualifier is most cost-efficient with no hard latency SLA, and the corpus is well past 10 million vectors. The documented decision rule says storage optimized is right when you have 10 million or more vectors, can tolerate the extra latency, and need cost efficiency, roughly 7 times cheaper than standard at this scale. Triggered sync compounds the savings by avoiding always-on streaming compute. Question 3. A team has integrated 3 tools into their Databricks agent: a Unity Catalog vector search index they own, a partner REST API behind a static bearer token, and a legacy mainframe system requiring a custom Python wrapper with stateful session handling. With the least implementation effort, how should these be hosted as MCP servers? Is it A, all 3 as custom MCP servers deployed as Databricks apps for consistency? B, all 3 as external MCP servers through Unity Catalog HTTP connections? C, vector search as managed MCP, partner API as external MCP, mainframe wrapper as custom MCP? Or D, vector search and partner API as managed MCP, mainframe wrapper as external MCP? Take a moment. The answer is C. Walk the ladder. Managed first, external second, custom last. The vector search index is a native Databricks asset, so managed MCP. The partner REST API fits the external MCP pattern with shared principal auth through a UC HTTP connection. The stateful legacy mainframe doesn't fit either pattern, so custom MCP earns its complexity there. Option D fails because external MCP requires HTTP transport, which a legacy mainframe with stateful sessions doesn't provide. Question 4. A RAG agent's nightly evaluation shows answer correctness has dropped from 92% to 78%. Retrieval relevance is steady at 88%, and groundedness is steady at 94%. The team is considering a larger generator model. What is the most likely root cause, and what should they investigate first? Is it A, the generator is hallucinating despite high groundedness, upgrade to a larger language model immediately? B, retrieval sufficiency may have dropped, the retrieved documents are relevant but no longer contain enough information to fully answer? C, the judge calibration drifted, realign the LLM judges against fresh expert-labeled examples? Or D, the Eval dataset is stale, refresh the expected facts labels to match new ground truth? Take a moment. The answer is B. When relevance and groundedness are both healthy but correctness drops, the missing leg is retrieval sufficiency. The retrieved documents are on topic but no longer contain enough material to fully answer. The fix is upstream, improve chunking, expand the retrieved set, or add a re-ranker, not a bigger generator. This is the exact diagnostic pattern Dino used in episode 18. Question 5. A company calls a third-party language model directly from their application code for production traffic. An auditor requests per tenant cost chargeback, an inference table for audit, and centralized rate limits across all model traffic, with the least operational overhead. What is the right architectural change? Is it A, build a custom proxy service in front of the third-party language model that logs requests to Delta tables and enforces rate limits in application code? B, configure AI gateway directly against the third-party language model's API endpoint, bypassing model serving? C, wrap the third-party language model as a model serving external model endpoint and enable AI gateway features on it? Or D, migrate the workload to a foundation model API endpoint, since AI gateway only governs Databricks hosted models? Take a moment. The answer is C. AI gateway is the control plane wrapped around model serving. It only governs traffic that transits a serving endpoint. Wrapping the third-party model as an external model endpoint routes the traffic through serving, and now inference tables, rate limits, and guardrails apply automatically with no application code change. AI gateway can't be pointed directly at an external API, and you don't need to migrate to a foundation model API. External model endpoints handle this case cleanly. And that's a wrap on production patterns. 10 decisions senior Databricks GenAI engineers get right. If this helped, subscribe for the rest of the Databricks GenAI Engineer Cert series. It helps me keep making these lessons free, and I'll see you in the next one.